Dr. M. P. Jayaraman is an assistant professor in mathematics in L.N. Government College, Poneri. He has specialized on geometric function theory. With 14 years of teaching experience, he has handled topics on probability and queuing theory, discrete mathematics, random process, and engineering mathematics. Being a recognized supervisor for guiding PhD and MS students of Anna University, he is the reviewer of the journal Computer Mathematics and Applications. He has also written books on discrete mathematics and has also published papers in 28 international publications, in 4 national publications, and has presented papers in 2 international and in 2 national conferences.
Welcome you all for UGC lecture series in mathematics. In today's session, we shall deal with the problem of constraint optimization problem. That means, we are interested in solving a nonlinear programming problem in which all the constraints of equality type. For that, in this episode, first we define the bordered Hessian matrix for a given nonlinear programming problem. Then, with the help of this bordered Hessian matrix, we state sufficient condition for a given NLPP to have an optimum solutions. Next, with the help of this necessary and sufficient condition, we are going to solve the given NLPP. First, consider the nonlinear programming problem, which is maximize or minimize the objective function f of x subject to the constraint h I of x equal to 0 for I equal to 1 to m. Our given NLPP has 2 constraints, then we have h 1 of x and h 2 of x. Given NLPP has 3 constraints, then we have h 1 of x, h 2 of x, h 3 of x. So, our aim is to solve this nonlinear programming problem of all the constraints of equality types. We have one and more than one constraints. We know very well, to solve a NLPP, to find the necessary condition, first we have to form a Lagrangian function in terms of Lagrangian multipliers. For the given NLPP, the Lagrangian function L of x comma lambda is f of x minus summation I equal to 1 to m lambda I into h I of x. So, for a nonlinear programming problem involving more than one constraint, our Lagrangian function in terms of the Lagrangian multiplier lambda is f of x minus summation I equal to 1 to m lambda I h I of x. Now, to obtain the necessary condition for a given nonlinear programming problem, it is enough to find the necessary condition for the Lagrangian function. From this Lagrangian function, these two equations dou L by dou x j equal to 0 for j varies from 1 to n and dou L by dou lambda I equal to 0 for I equal to 1 to n gives the necessary condition for given NLPP to have an optimum value of z, that is maximum z or minimum z. So, these two equations dou L by dou x j equal to 0 and dou L by dou lambda I equal to 0 gives a necessary condition for a given NLPP to have an optimum solutions. With this necessary condition, now let me define the notion of bordered Hessian matrix first. Now, we are going to state the sufficient condition in terms of the bordered Hessian matrix. For that, let me define the bordered Hessian matrix first. Suppose our NLPP in terms of n variables, the objective function in terms of n variables and m constraints, all are equality constraints. So, m constraint. So, consider a NLPP of n variables and m constraint, then the corresponding bordered Hessian matrix is of order m plus n cross m plus n. So, for an NLPP involving n decision variable and m constraints, the corresponding bordered Hessian matrix of order m plus n cross m plus n. Now, this bordered Hessian matrix has 4 blocks. Let me split the block in such a way. So, the bordered Hessian matrix has 4 blocks. The first block O represents a null matrix of order m cross m. So, in the border Hessian matrix, the first block O is a null matrix of order m cross m. If suppose our nonlinear programming problem has two constraints, then order of this null matrix is 2 cross 2. The next block is U. What is U? U is partial derivative of the constraints with respect to x j. If we take a first constraint as h 1, then dou h 1 of x by dou x j is the first row of the matrix U. Then dou h 2 x of dou x j is the second row of the matrix U. So, U is partial derivative of the constraint with respect to the decision variable. So, U is the partial derivative of the constraints dou h I of x with respect to the decision variable dou x j. Now, this order of U is m cross n. So, the matrix U is of order m cross n, where m is the number of constraints, n is the number of decision variable. Once you will get U, if we get transpose of U, we will get U transpose. So, the third block is transpose of the matrix U. Since U is of order m cross n, U transpose is of order n cross m. The final block V is again a matrix, and the order of the matrix is a n cross n matrix. Now, what is V? V is dou squared L of x comma lambda by dou x I dou x j. So, V is the matrix of second order partial derivative of the Lagrangian function with respect to the decision variable dou x I dou x j. So, order of V is n cross n. So, for a given nonlinear programming problem, first we have to construct border Hessian matrix to talk about the sufficient condition. The border Hessian matrix is of order m plus n cross m plus n. The border Hessian matrix has 4 blocks. The first block is O, which is a null matrix of order m cross m. The second block U, U is partial derivative of the constraint with respect to the decision variables, which is of order m cross n. The third block is U transpose, which is a transpose of the matrix U. The fourth block is V matrix of order n cross n. What is V is second order partial derivative of the Lagrangian function with respect to dou x I dou x j. So, once with the help of the given NLPP and with this definition of border Hessian matrix, once we get the border Hessian matrix, now we state the sufficient condition for a given NLPP to have an optimum value of z. The sufficient condition is as follows: let x naught lambda naught be the stationary point of the Lagrangian function L of x comma lambda. For a given NLPP, we construct a Lagrangian function in terms of Lagrangian multiplication lambda. For that Lagrangian function, let x naught lambda naught be a stationary point. Now, at this stationary point, we should construct the border Hessian matrix. So, let h b naught be the value of the border Hessian matrix computed at the stationary point x naught lambda naught. So, for a given NLPP, first we construct Lagrangian functions with the Lagrangian multipliers lambda. For that Lagrangian multipliers, we compute the corresponding border Hessian matrix h b naught at this stationary point. Then x naught is a maximum point if starting with principal minors of order 2 m plus 1, the last n minus m principal minors of h b naught form an alternating sign pattern starting with minus 1 power m plus 1. So, that stationary point x naught takes the maximum value if the principal minors of order 2 m plus 1 to last n minus m principal minors of h b naught forms an alternating sign pattern. The first principal minor should have the sign of minus 1 power m plus 1. For example, our NLPP have 3 decision variable and 2 constraints, then the first principal minors of the border Hessian matrix should have the sign of minus 1 power 3 plus 2, which is minus 1 power 5 minus 1. So, the first principal minor should start with the negative sign, then the next principal minor should have a positive sign in such a way that plus minus comes alternatively. Then this x naught will be a minimum point if starting with the principal minors of order 2m plus 1, the last n minus m principal minors of Hp naught have a sign of minus 1 power m. So, that stationary point x naught will be a minimum point if starting with the principal minors of order 2m plus 1 to the last principal minors of order n minus m have a sign of minus 1 power m. For example, our NLPP has 3 decision variable and 2 constraints, then minus 1 power m value is minus 1 power 2, which is 1 a positive signs. So, for a 2 constraint nonlinear programming problem, the sign of border Hessian matrix have positive value. Now, with this sufficient conditions and already known the necessary condition, now we try to solve a nonlinear programming problem with one and more than one constraints. The first problem is solve the nonlinear programming problem of minimizing z equal to 2x1 squared minus 24x1 plus 2x2 squared minus 8x2 plus 2x3 squared minus 12x3 plus 200 subject to the constraints x1 plus x2 plus x3 equal to 11, where all the decision variable x1, x2, x3 are non-negative. So, the given nonlinear programming problem involving 3 decision variable x1, x2 and x3 and 1 equality constraints. For this nonlinear programming problem, the n value number of decision variable will be 3 and the number of constraint m value is 1. So, for this nonlinear programming problem, the decision variable is 3 and 1 equality constraints, therefore, n value is 3, m value equal to 1. Now, we try to solve this nonlinear programming problem with the help of the necessary and sufficient condition. Let us have a break. Welcome back. Before break, we state the necessary condition for solving an NLPP and the sufficient condition in order to get the optimum value of f of z in terms of bordered Hessian matrix. Now, with the help of this necessary and sufficient condition, we try to solve a problem. For the given problem, the Lagrangian function is L of x1, x2, x3 lambda is 2x1 squared minus 24x1 plus 2x2 squared minus 8x2 plus 2x3 squared minus 12x3 plus 200. This is our function f of x1, x2, x3 minus lambda into h of x1, x2, x3, which is nothing but x1 plus x2 plus x3 minus 11 equal to 0. Now, in order to get the necessary condition for this Lagrangian function, we have to compute dou L by dou x1 equal to 0 and dou L by dou x2 equal to 0 and dou L by dou x3 equal to 0 and finally, dou L by dou lambda equal to 0. So, for that first dou L by dou x1 equal to 0 gives us the partial derivative of this function with respect to x1, which is 4x1 minus 24 minus lambda equal to 0. The next condition dou L by dou x2 equal to 0 gives us the partial derivative of this function with respect to x2, which is 4 x2 minus 8 and minus lambda equal to 0. And the third condition dou L by dou x3 equal to 0 gives us 4 x3 minus 12 minus lambda equal to 0. And the final condition dou L by dou lambda equal to 0 gives us minus of x1 plus x2 plus x3 minus 11 equal to 0. We name this equation as 1, this is 2, this is 3 and this is 4. So, the necessary condition is for the given nonlinear programming problem is dou L by dou x I equal to 1 to 3 equal to 0 and dou L by dou lambda equal to 0. Now, equation 1 gives us the x1 value equal to lambda by 4 plus 6. From equation 1, 4x1 equal to lambda plus 24, which gives us x1 equal to lambda by 4 plus 6. And from equation 2, that is dou L by dou x2 equal to 0, we got the equation as 4x2 minus 8 minus lambda equal to 0. From this, we got our x2 value as x2 equal to lambda by 4 plus 2. And from the third equation, that is 4x3 minus 12 minus lambda equal to 0, we get the value of x3 as lambda by 4 plus 3. So, from the equation 1, 2, 3, we got the value of x1, x2, x3. Now, in order to find the value of x1, x2, x3, we need the value of lambda. For that, by making use of this equation 4, with the help of this 3 value, we will get the lambda value. Now, substitute these 3 value x1, x2, x3 in equation 4, then equation 4 implies minus of lambda by 4 plus lambda by 4 plus lambda by 4 and 6 plus 2 plus 3, which is 11 minus 11 equal to 0. So, by simplifying this equation, we will get 3 lambda by 4 equal to 0, which gives us lambda value equal to 0. So, by making use of these 3 equations in equation 4 implies that the lambda value equal to 0. By taking lambda 0 equal to 0 in this equation x1, x2, x3, we will get the x1 value as 6, x2 value equal to 2 and x3 value equal to 3. So, with lambda equal to 0, the stationary points value x naught value is 6, 2 and 3. So, with the help of this necessary condition in terms of Lagrangian function for the given NLPP, the stationary point is x naught equal to 6, 2, 3. Now, we have to discuss about the sufficient condition for this nonlinear programming problem. So, to talk about the sufficient condition, first we have to construct the bordered Hessian matrix for the given nonlinear programming problem. This nonlinear programming problem is of 3 decision variable and 1 constraint. Therefore, n value equal to 3 and m value equal to 1. Therefore, the corresponding bordered Hessian matrix is of order 3 plus 1, that is of order 4 cross 4. So, in this bordered Hessian matrix, this matrix into 4 blocks. So, we have this matrix. So, since m value is 1, the first block is a null matrix 0 of order 1 cross 1. Next, we have to construct the matrix U. U is nothing but dou h x1 dou h by dou x1. Therefore, we have for this problem we have this U matrix is 1 1 1, because we know U equal to dou h by dou xj. Now, our h of x is x1 plus x2 plus x3. So, dou h by dou x1 is 1, which we placed here, and dou h by dou x2 is also 1, which placed here, and dou h by dou x3 is 1, which is placed here. So, it is of order 1 cross 3. Then this block is of U transpose. Our U is a 1 cross 3 matrix. Therefore, U transpose is 1 1 1. Next column is V. What is V? V is dou squared L of x comma lambda by dou xi dou xj. So, V is the matrix of second order partial derivative of the Lagrangian function L with respect to the decision variable dou xi dou xj. Now, for this problem, the dou squared L by dou x1 we have as 4, dou squared L by dou x1 dou x2 0, dou squared L by dou x1 dou x3 0. Therefore, the first row of V is 4 0 0. Next, dou squared L of dou x2 with respect to x1, x2, x3. So, dou squared L by dou x1 dou x2 gives us the value 0. Therefore, in this place we will put 0. Then dou squared L by dou x2 is 4. So, in this place we will put the number 4. Then dou squared L by dou x3 dou x2 value is 0. Therefore, in this row we will get 0. Next, the third row of V is dou squared L by dou x1 dou x3, which the value of dou squared L by dou x1 dou x3 is 0. So, in this place we will put 0. Then dou squared L by dou x2 x3 is also 0. In this place we will put 0. Then dou squared L by dou x3 is 4. In this place we will put 4. So, for a NLPP with n value equal to 3 and m equal to 1, the first null matrix is of order 1 cross 1. Then U matrix is of order 1 cross 3, U transpose is of 3 cross 1, and the V matrix, that second order partial derivative of L with respect to the decision variable, is of order 3 cross 3. So, for you, with the help of this Lagrangian function, we construct the border Hessian matrix HB naught for the given nonlinear programming problem. Now, for this NLPP, the number of constraint is 1, therefore, m value is 1. Now, for this problem, the n minus m value, which is 3 minus 1, which is 2. Therefore, the minimum value of the given f of z should have a sign of minus 1 power 2, which is plus 1, a positive sign. So, in order to get the sufficient condition, it is enough to find the determinant value of this border Hessian matrix should have a positive sign. Now, we try to find the determinant value of this border Hessian matrix. We find the determinant along this row. The first entry is 0, therefore, we have 0 into something. So, it will become 0. Then the next one is minus 1 into, the minor for this one is 1 0 0 1 4 0 1 0 4. So, for this one you omit this entry corresponding rows and corresponding column, we will get the minor as 1 0 0 1 4 0 and 1 0 4. The next entry is plus 1 into, by omitting the corresponding row and column, the remaining matrix 1 4 0 1 0 4 and 1 0 0 and 1 0 4. And for this one, minor is, by omitting this row and column, we have 1 4 0 1 0 4 and 1 0 0. So, for this border Hessian matrix, we are interested in finding the value of this determinant. For by expanding through the first row, we will get the matrix as this one. Now, from this matrix, it is clear that the value of this matrix is 16, therefore, minus 1 into 16 minus 16, and value of this matrix, by with the help of matrix determinant, we will get the value as minus 16, and this matrix also will get minus 16. Therefore, the determinant value of HB naught is minus 48. Here the m value is 1, therefore, minus 1 power 1 is negative sign, minus 1. So, since the determinant value of the border Hessian matrix is negative, which gives the sufficient condition as the given NLPP has minimum z, with the value of x 1 equal to 6, x 2 equal to 2 and x 3 equal to 6, we get the minimum value of z. The next problem is minimize z equal to 6 x 1 squared plus 5 x 2 squared subject to the constraints x 1 plus 5 x 2 equal to 3 and the decision variable x 1 x 2 greater than 0. So, the given NLPP involving two decision variable and with an equality constraints. Therefore, n value for this problem is 2 and m value for this problem is 1, where m equal to number of constraints, n equal to number of decision variables. Now, in order to get this necessary condition, first we will construct the Lagrangian function for this problem, which is nothing but L equal to 6x1 squared plus 5x2 squared, this is for the function f of x, minus lambda into h of x, which is nothing but x1 plus 5x2 minus 3. Now, the necessary condition for this given NLPP is dou L by dou x1 equal to 0, which gives us 12x1 minus lambda equal to 0. And the next condition is dou L by dou x2 equal to 0, which implies 10x2 minus 5 lambda equal to 0. And the final condition dou L by dou lambda equal to 0, which implies minus of x1 plus 5x2 minus 3 equal to 0. We name it as equation 1, 2 and 3. So, the necessary condition of dou L by dou xi I equal to 1 to 2 and dou L by dou lambda gives us these 3 equations. Now, from equation 1 we have x1 equal to lambda by 12, and from equation 2 we simplify this equation as 2x2 minus lambda equal to 0. So, from equation 2 we have x2 equal to lambda by 2. Now, by substituting this x1 x2 in this equation 3, we will get the value of lambda. So, we will substitute this x1 x2 in equation 3, we have lambda by 12 plus 5 lambda by 2 minus 3 equal to 0. Now, by simplifying this equation, we have, by taking LCM, we have 12. So, lambda plus 6 into 5, that is 30 lambda minus 36 equal to 0. So, from this we have 31 lambda equal to 36, which gives us lambda equal to 36 by 31. So, by substituting this x1 x2 in equation 3, equation 3 gives us the value of lambda equal to 36 by 31. Now, with this lambda we got the x1 value as, by substituting this lambda in x1 we will get 36 by 31 by 12 is your x1, which is nothing but 3 by 31. Now, our x2 value, with the help of this x2 value is 18 by 31. Now, by substituting this x1 x2 in the subjective function, we will get minimum z equal to 54 by 31. Now, with the help of this border Hessian matrix, we can easily verify the sufficient condition for this nonlinear programming problem. Since our m value equal to 1, the value of the border Hessian matrix should have a sign of minus 1 power 1, which is a negative. So, the border Hessian matrix at this stationary point gives us the negative value. Let me recap. The necessary condition for the given nonlinear programming problem should satisfy the condition of dou L by dou xi equal to 0 and dou L by dou lambda equal to 0. The border Hessian matrix is a square matrix which has 4 blocks. First block is of null matrix, second block U is the partial derivative of constraint with respect to the decision variable, the third block is transpose of U, and the fourth block V is second order partial derivative of L with respect to the decision variable xi and xj. With the help of this border Hessian matrix, the stationary point x naught is maximum if the principal minors of order 2m plus 1 to the last n minus m principal minors to form of HB naught have a sign of minus 1 power m for a minimum point, and for the maximum point the sign pattern is alternating with the starting sign of minus 1 power m plus 1. The exercise question is minimize z which has this value subject to the constraint 2x1 minus x2 equal to 4 and x1 x2 greater than or equal to 0. Thank you.